Hello, my name is Sean Singleton, and this is an introduction to analytical chemistry. Analytical chemistry seeks ever improved means of measuring the chemical composition of natural and artificial materials. The techniques of this science are used to identify the substances which may be present in a material and determine the exact amounts of the identified substances. It is the science of chemical measurements. Wilhelm Ostwald was a German chemist who received a Nobel Prize in Chemistry in 1909 for his work in catalysis, chemical equilibria, and reaction velocities. The following is a famous quote on the role of analytical chemistry. Analytical chemistry, or the art of recognizing different substances and determining their constituents, takes a prominent position among the applications of science, since the questions it enables us to answer arise wherever chemical processes are employed for scientific or chemical purposes. In analytical chemistry, there are two main types of analysis: quantitative analysis and qualitative analysis. Qualitative analysis can be described as providing information on the identity of the substances contained in matter, while quantitative analysis provides information on the quantity of a substance in matter. Simply put, quantitative analysis tells us how much of a substance is in a solution, while qualitative analysis tells us the identity of a substance. Analytical chemistry was being performed long before the advances in modern instrumentation. Modern instruments are often based upon wet chemistry methods, but have been automated and made more precise. Wet chemistry uses known chemicals to react with unknown chemicals, or known amounts of chemicals with an unknown amount of chemicals, and uses known reaction results to determine what or how much of a chemical is present. One common wet chemistry technique is titrations. A titration takes a known chemical reaction that typically results in a change of color, because color change is easy to identify. By carefully measuring how much of a titrant is needed before the color change occurs, we can calculate how much of the other compound is present. Next we have a flame technique. So each element burns at a very specific color. By burning the elements and watching the colors, we can determine what elements are in a compound. There are many different types of chemical methods used in analytical chemistry. These tests are usually qualitative. For example, the Kastle-Meyer test can determine if there is any blood present by swabbing an unknown area with hydrogen peroxide and observing if it rapidly turns pink. Other tests such as chromatography can isolate specific compounds. This method isolates compounds based on their size or charge. A chromatography column is prepared with substances that are meant to retain some products and let others fall through. It can be thought of as a complex molecule filter, allowing the various components of solution come out at various times. These substances can then be further analyzed. There are several different ways to quantitatively describe the concentration of a solution. Each has its own appropriate application. Molarity can be defined as the number of moles of solute per liter of solution. It is used for quantitative reactions in solution and titrations. One example of this is when determining the quantity of acetic acid in vinegar. Mole fraction can be defined as the number of moles of solute per total moles present. This is used for partial pressures of gases and vapor pressures of some solutions. Molality can be defined as the number of moles of solute per kilogram of solvent. It is used in determining how colligative properties vary with solute concentration. In regards to molality and molarity, if the solvent is water and the concentration of solute is fairly low, molality and molarity are approximately the same. 1 liter of water weighs approximately 1 kilogram. The mass percentage can be defined as divided by the mass of solution multiplied by 100. This is useful when masses are known but molecular masses are unknown. The remaining three on this chart are simple parts ratios. An example of when parts per billion will be used is when determining the amount of lead in tap water. The electromagnetic spectrum can be described as the entire distribution of electromagnetic radiation according to wavelength. Although all electromagnetic waves travel at the speed of light in a vacuum, they do so at a wide range of frequencies, wavelengths, and photon energies. The electromagnetic spectrum comprises the span of all electromagnetic radiation and consists of many subranges, commonly referred to as portions, such as visible light or ultraviolet radiation. The various portions bear different names based on the differences in behavior in the emission, transmission, and absorption of the corresponding waves, and also based on their different practical applications. There are no precise accepted boundaries between any of these portions, so the ranges tend to overlap. The entire electromagnetic spectrum, from the lowest to the highest frequency, includes radio waves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Nearly all frequencies and wavelengths of electromagnetic radiation can be used for spectroscopy. Spectroscopy is a branch of science concerned with the investigation and measurement of spectra produced when matter interacts with or emits electromagnetic radiation. Absorption refers to how much light or other waves can be taken in by the material being measured. Emission, on the other hand, refers to how much light or other waves can be released by the material being measured. Emitted light is usually altered from its original state by the material, and that altered light is what's measured during spectroscopy. Absorption spectroscopy can be defined as a procedure that uses the absorption of light waves by free atoms to determine chemical elements. Ultraviolet visible spectroscopy refers to absorption spectroscopy in the ultraviolet visible spectral region. This means it uses light in the visible and adjacent ranges. The absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. In this region on the electromagnetic spectrum, atoms and molecules undergo electronic transitions. Absorption spectroscopy is complementary to fluorescence spectroscopy, in that fluorescence deals with transitions from the excited state to the ground state, while absorption measures transitions from the ground state to the excited state. Infrared spectroscopy relies on the principle of specific bonds vibrating at a unique frequency when subjected to infrared light from which the absorbance is measured to identify the substance. Magnetic resonance spectroscopy, or NMR spectroscopy, is a spectroscopic technique to observe local magnetic fields around atomic nuclei. These fields are highly characteristic to individual compounds. Flame spectroscopy relies on the principle that an alkali metal salt drawn into a non-luminous flame will ionize, absorb energy from the flame, and then emit light of a characteristic wavelength as the excited atoms decay to the unexcited ground state. When choosing a method to analyze a substance, you must ask yourself a number of questions. To what sensitivity do I need my results? What range are my results going to be in? What are my resources regarding time and money? Or which instruments are already available? Which methods are appropriate for the type of chemical I am analyzing? This table is a rough guideline which will help choosing a method.